Okay, well, we're working on a problem here. We've got two discs. This isn't physics class, but of course, this is going to have a lot of application of physics. Have an electric field in between these things and the field density, and we want to calculate total energy or something. Okay, we have to do it. Okay, well, what we're really looking at, okay, this is sitting flat on the table a minute ago. And we had an origin over here. And we wanted to describe just one of these disks. Okay. So how do we do that? Well, everybody did their own eyeball to determine what coordinates of this thing were. Okay. And most people came up with a center at something like 25 centimeters, and 25 centimeters, 28 centimeters. This one, right? In X, Y, and Z, this would be X, this would be Y, this would be Z. So it'd be Y equals, say, 20 something. Z equals 20 something. Okay, and X equals whatever X is. That would be probably 20. Okay. It just depends where this is center. And all of that is kind of arbitrary, but we don't want any of it to be zero. And then there won't be reality. Nothing zero there. So we have a disk. Let's say the center is 23. 36. Okay, those wouldn't be very good numbers, but they're still the same ballpark. Okay. The X is constant because the thing's oriented like this, and the X-axis is here. It's perpendicular to the XY plane or the XC plane. Okay. It's a perpendicular. Yeah, it's parallel to the YZ plane. X is constant. So X is constant. Radius is 10, this is in centimeters, that is what the radius is. Okay. So what's the circle? Oh. The equation of the circle. Just using Pythagorean theorem, where I'm not even going to write it down. If you haven't done this a few times, the circles, then you haven't done the homework. Then no, you all have done the homework. Okay. Now, how much help you had on the homework? From examples and so forth, did you really internalize what you did in the homework? Because you're going to hope you did. Because we're getting into integration of 3 dimensions. Later on, we're going to get to the parameterizing surfaces. Later this month. Okay, that's the toughest thing. So we're just trying to develop the idea of an integral in 3 dimensions. Okay, so you started right down to it, which is great. Okay, it's a good extension. I'm not sure anything that we do as far as just describing this disk is going to involve a triple integral. Is in a few minutes. Okay, so if you thought about triple integrals, that's good. Okay, so we're just doing the disk. Now, I want this described, this is a sort of, this isn't the disk. We want this described by inequalities. Now, you've been describing regions by inequalities, incidentally, a lot of people, and this concerns me a little bit. A lot of people wanted to describe this as X goes from, or sorry, Y goes from 16 to 36. And then Z goes from 20 to 40. That's a square. If you don't do that, that's not the way we've done it. And a lot of people are starting to write down partitions, which is really good. Okay, there's some efficiencies here that naturally, because first assignments you had, we had to do this was in the full grade and stuff like that. You might be a little rusty. Get over it. You really want to get over it because you're going to again have to break these things down in 3 dimensions. Okay, so we do a picture. That's going to be a good circle length. Surface with my hand and flatten out. Dang, that was going to be an epic circle. Okay, so here's a circle. Here's the center. Here's Y. And here's Z. Here's the equation of the circle. Well, if the Y coordinate of the center is 26, then the Y coordinate here is 16, and the Y coordinate here is 36. So Y goes from 16 to 36. Now you have Z coordinates that do go from, let's see, what's Z 30, from 20 to 40, but not for every cross section. Cross sections look like this. So a typical cross section. Put a Y here. Here's your typical cross section. Y doesn't go from 20 to 40. It does if your cross section right here, but that's only for that one cross section. Okay, so where does Y go? Where does it start? Where does it end? Well, I can do a split little right triangle here. Side is Y. Side is M. And what did that two come out so small? That's fine. Okay. Now, everything you do is certainly going to involve that triangle, one way or another, or something totally analogous to it. Okay, it's a circle. There you have it. It's a different function. Well, you can still do a triangle. Okay, or something very similar. So it's a square root of 100 minus y squared. So that at this point, then it's, yeah, Z equals 26, no, 30, darn it. It'll look before, 30. Minus y squared at this point. Then down here, I'm not even drawing the triangle because of the symmetry of the situation, but I still recommend if you're doing it, you draw the triangle and make sure you understand on both sides. And generally, you'll be bounded above by a different function, you'll be bounded below by. Okay, and you've seen that. You've had it in your homework. So now we can describe this by Doesn't have room to write everything under the square root, but it goes from here to here. Right? So you know what I'm going to write there. Even though I'm never going to write it because I can't write on there. Okay. There's. So if I wanted to integrate something over the disk, I didn't ask you to do that, but if you wanted to integrate the area of the disk, let's say. You to go for the area. If you had a density here, you could multiply the area increment by the density at sample point, and your density function would insert right into your interval. Okay, and you should be familiar with all of that. What's coming here in a few minutes. Okay, so that's just a review of essentially what you did for homework. Now, I think you have integrals in polar coordinates, right? Well, to do a polar coordinates, I'd shift the origin to this point. And you just have 0 less than or equal to r less than or equal to 10. And 0 less than or equal to theta less than or equal to 2 pi, wouldn't it? So polar coordinates, if you put the center there, make this really easy. Okay. It's the natural set of coordinates you would use. Now, since everything we do today is going to be rectangular coordinates, but then next time it's going to be spherical and cylindrical coordinates. So we want to kind of anticipate that a little bit. Okay. So right now we're going to work in rectangular coordinates, but by shifting the origin to this point, you can take that region and all kinds of things. Now I want to move into 3 dimensions because, of course, the region between these two plates. Ouch. I got stuck. I got a boo-boo on my pinky finger. This little dog didn't even pay much attention to when he's licking my hands. Okay, it's a good boo-boo. He don't want to go after it. Yeah, infections and stuff. It's coming out the door to the LRC building and opened the door. And somehow did it clumsily, I think having to do with this thing. Okay, it stuck or something. And it kind of got caught in between the handle and the door frame. Yeah, it was just one of the, oh, dang, what happened? Went on. It never did bleed much. So you don't have to send a sympathy card or anything. Although if you want to, seriously. So I just got my finger caught in there. Let's begin closing. Okay. Now you want to do the region between these two. Okay. Well, you've already got this one described. Okay. X goes from whatever it is here to whatever it is here. How far is that? Well, it's probably less than the radius. Say it's, you can make your own estimate. Okay. How far is it from here to here? And now, how would you describe this 3-dimensional region between these plates? Everybody think? Well, well, attempt to clarify. Okay, well, let's just say X is, hey, I'm going to look. Okay, now put this down. What I see, X goes from about 18 to 25. Well, that was about 7. Okay, so now the 3-dimensional region. That's a bad question. Okay, now it's better. Okay. So this is in a plane parallel to the YZ plane. So is this. And this point projects down and over, so X goes from here to here. I said from 18 to 25. You can say whatever you want to say. As long as you don't have this thing 14 kilometers between the plates, because that would work. Okay, so this disk we have the inequalities we have here. Now, for every point between here and here, okay, some point here projects over to some point on this disk, right? Okay. As long as the Y and Z coordinates satisfy these two inequalities, it's going to be in this region. And that's going to be true as long as X is between 18 and 25. If X is less than 18, then you're on this side of the two disks. If X is greater than 25, you're on that side. So now the full region is from 16 to 36. Let's see that. Okay. Had ambitions of actually being able to write this out, just didn't make it. Okay, so there are my limits in Z. Now for every Y between 16 and 36, and every Z between here and here, there's a point on this disk, and there's a line between this disk, with X values between 18 and 25. And every point on that line is within the region bounded by the two disks. Okay. So we can say that it's between 18 and 36. Okay. What's the volume? The volume of that region is the integral 16 to 36 of the integral from 30 minus that square root to 30 plus that square root. We know what's under the square root of the integral from 1825. This integral is the integral for X. The inequality gave us this is for Z. And the 16 to 36 are the limits on Y. An easy enough integral. If you do a trig substitution after the So, you know, in your Y. And that's going to give you the volume. And if you do that, it's area of the base, which is 10 pi squared, centimeters squared, times the altitude, which is perpendicular to the base. Altitude is horizontal. We usually think of altitude as vertical. Get over it. It's perpendicular to your base. Okay. So it's 70 pi squared. So I should be able to do that anyway. Now, if I wanted to integrate, let's say, a density, let's say we have a charge density. Equal to 2xy square root of z. Okay. Then in any increment, total charge is going to be this. Is the volume of the increment times the charge density being in charge per unit volume. I use charge. This is what we talk about charge in physics. Maybe we want to think mass density. It could also be a mass density, right? Mass per unit of volume might be more intuitive if you're not in physics, okay? Of whatever density. Okay. So let this be a whatever density. Okay. Get this. This implies that's a total charge. Whatever. Contribution of the instrument to the whatever. This implies whatever is the triple integral. Now I notice with this integral, and I can make this point since it comes to integral now. Both x and y have constant limits. Okay. If I could change the order, I could put x anywhere. Okay. So I could integrate from 18 to 25 from this to this, this to this, integrating x last. So I put my dx over here and put the dx anywhere I want to, because my x limits don't depend on y or z. one that depends on anything is my Z depends on Y, so I have to integrate Z before I integrate Y. And it should be clear to you why that is. Okay, so you want to change order of integration, you gotta be a little bit careful. Gets a little hairier when you got more complicated regions. You have to get the whole description of the region to see how you would change the order of integration. Okay, so the total of whatever is going to be the integral. That's going to actually be kind of convenient, except it's not really because. Yeah, kind of, that might work. That's actually probably work out. You get a y squared over 2 when you integrate with respect to y. And then you're going to be substituting. Oh, sorry, wait a minute. I got to substitute this from the integrated z. Not like for something that wrong one. As I said, you got to integrate y after you integrate z. Okay. Yeah, there are a few points. Now, what if we have the same region? Remove I'm going to make a cone out of this. Point up here, I'll take a line from this point down to this point. Okay, this point over to this point. Okay, actually this point, right? So that I end up with a double cone. Does that make sense? If I project every point here to the point symmetric with it over here, I get a double cone. So my like this. 40 centimeters. And this is a side view with the x-axis in this direction. And if you want to make a prettier picture, go ahead and okay. You make it look like of course, we got a dimension right there. But where do you want to put the origin? Gesture. Okay, well, I'd recommend putting the origin point in. Because then you're going to have a symmetry. And maybe, depending on what you're integrating, let's see, this is all. Depending on what you're integrating, you might have to only integrate half of this. If the function is symmetric between here and here, whatever function you're integrating, have a symmetry respect to x, then you get away with that. Okay, but let's describe this region. And let's just describe right now this now. Okay, so when things come to a point like this, and Assume 40 centimeters between this plate and this plate. Still 40 centimeter diameter, 10 centimeter radius. We can sketch this thing in an X, Y, Z coordinate system. And it's, so here's kind of what the half cone looks like. So a side view looks like this. Let's say we have an X star here. Then my question is, what are the limits on Y and Z? Well, if X star is fixed, that means we're in the plane X equals X star. That's a plane parallel to the YZ plane. So when we cut the thing, we get a circle. If we cut it here, we get a smaller circle than if we cut it here. So we're going to be able to get the radius of the circle very easily because, well, here's the radius of the circle. Okay, that's the radius of the circle we get when we cut this thing to the plane parallel to the plane for a constant X star. So what's the radius? Well, we have to take the dimensions of this thing. This is 20 centimeters here. And of course, it's 20 centimeters here. This is 20. And this is 20, right? Which means this is like, if this is a Z axis, like the line Z equals X, there's equals 1/2 X. Okay. And just by either that or by similar triangle, I'll do it by similar triangles because it's going to be my equation. I've got two similar triangles, so this one and this one. Okay. Two similar triangles, one triangle. And by 20, the other is somewhat smaller. It's X star. Down here, it's a similar triangle. So this is, I call this R, this is the radius of the circle that I get when I cut this thing. And R over X star has to equal 10 over 20. So the radius is X star over 2. So now I've got a circle of radius X star over 2. Now, if I just want to volume this thing, if there's nothing dependent, like there is here with a density function on X, Y, and Z, I just wanted to get the volume. I just have to integrate pi times R squared, which is pi times X star squared over 4. Okay, or pi X, pi over 4 X squared. From 0 to 20, I get the volume. Okay, it'll just be a single integral. If I want to get in all this stuff, then I'm going to have to do tripling. Okay, if there's no Z dependent, I'm getting rid of the double. I don't know why. So, well, that's what I've got. So let's leave it. What works out. My region now is zero less than X, less than or equal to X, less than or equal to 20. And I could say 0 less than or equal to R less than or equal to X over 2. And 0 less than theta less than 2 pi. That's equal. Okay. And mix up my coordinates. You know, rectangle and polar coordinates all mixed up, right? Well, probably don't want to do that. If he does, you have to be careful. Especially if you got a function here. Your variables get all mixed up. It'd be hard to isolate. You never pretty much never want to do that. Okay, the point is, we got to parameterize the circle, or we got to put inequalities in the circle. But that's pretty easy to do. We could go from negative x over 2 to x over 2, right? And then what's y do? So now I've described the circle of radius x over 2 for every value of x. That leads me to my area. Okay. Does that make sense? Got to integrate with respect to y, and I'm going to get z's. What am I going to get? I'm going to get negative 100 minus z. Okay. I get 2 times the quantity 100 plus z squared. I got to integrate that with respect to z. I'm going to let z equal sign this tangent. Okay. I'll let you figure that one out. You've got to review the integration. But 1 plus tangent squared. Then I integrate with respect to z, and I'll be able to substitute my x's in for z. And then I can integrate with respect to x. So, okay. If there's a function that can be integrated over this region, I can do that. And now, I've used this one example because I want to do this in a good bit of detail. There's a lot more that can be done. You're going to need to read your text, but if you understand this, it'll make the text, I think, pretty accessible. Text starts out with partitions. Okay, this is everything in terms of partitions. Then it moves to a more general hand-waving thing, describe the region by inequalities. Notice I didn't even partition everything yet. Okay, once you understand partitions, if you understand them, you're safe doing this if you're careful. And usually it doesn't make any difference, but you want to understand what you're doing. There's stuff about changing the order of the I don't want to do that. Okay, let me just do this differently. Illustrate that. This region doesn't have to be described by exponent sections. I can describe this region equally well by saying y and z. So we can let z go from negative 10 to 10. And we can let y go from okay. Now what I've got there is this disk. What the text will tell you is you just imagine projecting the whole surface onto the onto one of the coordinate planes. Okay, so I project this whole surface onto the coordinate plane. I get that surface. Okay, so like there's a shadow. You know, put your light source over there at an infinite distance, make it infinitely bright, so we'll make sense. You get a shadow on the y-z point.
That's smart, yeah.
That's what I've described here. Now, it also describes this region if you let X equal 20, okay? But then then what happens to X? Well, for given Y and Z, I can call it crash here. Okay, I can project this line for in the actually plane, here's your panel, right? But the whole line isn't inside of the surface. Okay, so I've got to maybe look at this thing. At the end view, I've got a Y and a Z. So let's just say this is in the YZ plane. The YZ coordinate here is the same as the YZ coordinate here, same as YZ coordinate everywhere on this projection line. And here's the center of the disk. Well, it's like I've got an R equal to the square root of Y squared plus Z squared. Okay. Now, I can look at it. Find the distance R here. How far can I go before I hit the end? Okay. That makes sense? Okay, so if you take the Y and Z coordinates from this point, you know how far you are from the x-axis. And if you slice this thing through this point in the x-axis, it's still going to look like this. Okay. And you're still going to be the distance R. Okay. Question is how far you go here? Well, again, by similar triangles. You're going to have R here. And R is going to be in the same proportion to the X coordinate as n is 20. And so R is going to be half of your X coordinate. So then we can say, and I'm saying this kind of fashion, what did I go through? And I think I said that kind of wrong, but anyhow, X is going to go from I want to write 2R, and I'm going to write 2 times the square root of X squared plus Y squared up to 20. I'll try to make that a little clearer. Here's R. Here's R. And here's my X. Okay. Set up simple proportion. You can also do the equation of this line. Okay. Many different ways to do it. So you get this. So X goes from here to here. S goes from 2R to 20. R is just the distance at this point from the x-axis, which is y squared to y squared plus c squared. And I've got x squared plus y squared. I write them out. Intervention of conscious thought. Yeah, if you write that wrong and then try to do the integral, you're going to be in some pain. And be more careful than I am because I'm not actually going to do that. It's an easy. I mean, if you do choice substitution. Thank you.